So we're talking about Rao-Blackwell, and the idea here is if you have a sufficient statistic and you have a possibly randomized decision rule for your parameter estimate, and if the loss is convex in the second argument in the action estimator, then by conditioning on the sufficient statistic, your current decision rule, you get a better estimate. Or at least you don't do worse. So you do as good as the original one. And if the loss is strictly convex and this eta turns out to be different than delta, you get something which is strictly better. So you would make delta inadmissible. So this is a very nice result that ties sufficiency to the risk or the statistical performance. And it's just a consequence of applying Jensen's inequality. We saw that in this example, like this was an example, if you have sufficient statistic like max here for estimating theta, sorry, for this family, and then you have a particular not necessarily good estimator. A particular estimator based on sample means, then by conditioning on T, you would get a better estimate. So we saw that the variance of this, for example, is like drops quadratically, while the variance of the original one drops like 1 over n, and the biases are the same. So just an example that shows Rao-Blackwell is true. This I'm gonna skip. Another consequence of the strictly convex loss functions is that these basically risk functions are unique. So if you have among the admissible decisions, so if you have two different admissible decision rules, then they can't have the same loss function, but this is minor. Sorry, not the risk function. And then in this example, I'm going to also skip. This shows that Rao-Blackwell could fail if the loss is non-convex. So this is a particular example where we take the loss to be so-called epsilon sensitive loss. So if theta is closer to A than epsilon, then we don't pay the price. If it's bigger, we pay a flat price of 1. And in this binomial model, you can find a randomized decision rule, basically just flip a coin, that independent of the data. And then you can show that you can't beat this. It's like that uniform domination does not hold. So you can, no deterministic estimator can uniformly beat just the basic coin flip. Not that coin flip, but just uniform. So you predict this by a uniform 0-1 random variable. So I'll let you think about it. We'll go through this example and then try to argue this for yourself. What I'm going to do today is talk about that UMVU idea that we perhaps mentioned very early on. So if you recall the first few lectures where we introduced the decision theoretic framework, that the concept of risk functions, there was this issue of comparing risk functions in that they could be incompatible or incomparable because they're functions. So for two estimators, you get two different functions. And one idea to try to resolve this issue is to try to reduce the risk functions to numbers, which we'll do later. The other is to restrict the class of estimators. So this is what we plan to do now. So especially we'll focus on quadratic loss. for which you know that the risk has the bias variance decomposition. And we're going to restrict also to the class of unbiased estimators. So we set the bias to 0. And then ask if it's possible to get uniform domination among these classes. So is there an estimator that uniformly dominates all the other ones within this class of unbiased estimators? So that's what we want to do. So let's maybe formally define things. So let this UG be the class of unbiased estimators for G theta. So this G theta is back. It's like a little bit of generality. If you want to make things simple, just think of it as theta, but potentially you can estimate some other function of theta. And if you're interested in this particular function, G theta of theta, an estimator is unbiased, or decision rule is unbiased if this identity holds. The expectation of delta, again, this is a shorthand for delta x in G theta, and then this notation again is saying that I'm kind of sampling. So sampling x for p theta, taking the expectation under p theta, and this turns out to be equal to G theta for all theta. So no matter under which parameter we're taking the expectation, it's always so. So this is definition of unbiasedness. So this is the class of all decision rules that satisfy this unbiased condition. So we're restricting ourselves to this class. And if you recall, this function G is called U estimable or unbiased estimable if this class is not empty. If there's at least one unbiased estimable. So UMU is defined like this. An estimator is UMU for estimating G theta if first it belongs to this class, so it's unbiased. And then variance of delta is less than or equal to the variance of delta prime for all theta, and this should hold for all delta prime. Okay. So uniformly the variance, so uniform here, this is called uniformly minimum variance. So uniform here is uniform over all the parameters. Minimum variance is obvious, so it has the minimal variance. And then unbiased is also like this part. Okay, so uniformly minimum variance unbiased is that notion of domination. And because we're in the unbiased class, this also means that the risk is uniformly dominated the other ones. Sounds good? Definition is good. So this is a very strong property to ask. And similar thing in the testing, if you get where it's uniformly most powerful test, whenever you have some sort of uniform domination, it's generally a difficult condition. It may or may not exist. The interesting result is this result, oftentimes referred to as Lehman-Schiffin's theorem, that guarantees such a UMU estimator exists if you have a complete sufficient statistic for the family. So the families that admit a complete sufficient statistic. So suppose you have a family, there exists a complete sufficient statistic for this family, and this is a very mild condition that there exists one at least unbiased estimate. UG is non-empty. Then there exists an essentially unique UMU. This essential again up to measure theoretic almost everywhere. So there is essentially unique UMU for G theta, and it will be of the form HT. So it's going to be a function of the sufficient statistic. Okay. So the idea is that once you have a complete sufficient statistic, if it's possible to do unbiased estimation, then there is a uniformly variance unbiased. It's a pretty interesting result. Okay. This again, yes.
U and VU is not necessarily the minimum risk. Right?
It is necessarily minimum risk if you look at the quadratic loss. So for quadratic loss, the risk is just the MSE, right? So risk would be MSE. And it would be bias squared plus variance. So we are forcing this to be 0. So the risk is really just the variance in this class.
We in the class we were talking James Stein.
Right.
So I just make the connection that is.
So James Stein is not unbiased. Right. So this is not claiming that among all possible estimators, the risk is the smallest. Right. So that's not what we're saying. You're right. But if you restrict to this class, then there is some. Yeah. So that's the whole point. Right? It's not a general claim, but what we're saying is that within this class, the risk is uniformly complete. Great. Another question? So I'm going to try to prove this. The proof is sort of straightforward, and it uses similar ideas that we have seen whenever you have a complete sufficient statistic. It's good to condition on it. Whatever you have, you condition on it, you potentially get something better. By this point, it should be sort of quite familiar, this idea. So the idea is that I'm going to pick a delta in UG. So I get an unbiased system. I can just pick one. The set is non-empty, so there is one such estimator. Then I'm going to condition on T. So take the expectation delta given T. This is raw black validation because T is sufficient. And well defined by sufficiency. Hopefully by this point you understand what this means. So the eta is really the estimator, we need delta theta. Another claim is that this is especially unique to is pretty impressive result. Because you start from any unbiased estimator, you condition on T, you get the U and VU, and it's essentially unique. So the way it works, actually, the easiest to see is, so I have delta. I'm going to condition by this raw black valorization. I get eta. Okay. In order to show that this is U and VU, I'm going to actually start from some other delta prime, if there is one. If there is no other one, then you're done, because there's just one unbiased system. But let's say if there's another unbiased system, I want to show that this has a smaller variance than delta prime. What I'm going to do is that I'm going to do the same thing to this guy. So I'm going to do the raw black valorization. This comes down to eta prime. What we show is that these two are actually equal. And then we can complete the chain. So that's the plan. So take any delta prime. Eta prime is the raw vectorization of theta, like delta prime. And so I want to show that these first items are very equal. This procedure, no matter which one you start, ends up in the future. So the way we do it is form this expectation. And my claim is that this expectation is 0. So the expectation of eta, you can say eta x if you want, minus eta prime of x, this is 0. So why is that claim true? Sorry? So delta and delta prime are combined. What do you see?
Expectation becomes very same.
Yeah, so there's one step to note that this raw black valorization preserves expectation. So this conditioning by T does not change the expectation. Why? Power property. Was there a couple of usual suspects in this course, power property one. So by power property, the expectation is the same as delta, the expectation and the final is the same as expectation delta prime. And the expectation of delta and delta prime both are the same. By assumption, they're unbiased. So this is g theta basically minus g theta, which is 0. Identically for all theta. Right? So can I conclude something from this? These are also, I can write it as just a function of t to be a little more clear. Eta minus eta prime is an estimator, yes. It's like, it's unbiased for 0, but not unbiased for gt. So these are going to be functions of t because I'm conditioning on t. So now if you look at this, anyone wanted to? Yes.
Use completeness to get the function inside the expectation is equal to 0.
Yes, so this is some function of t. T is complete. So this is saying that function is first order ancillary. So it has to be constant equal to this value. So eta of t is, this is 0, like almost everywhere, by completeness. So that part we proved that this procedure produces the same statistic, like our estimate. Okay, yeah.
So is this only valid for a complete sufficient statistic or?
Yes.
Insufficient?
No, just complete. Yes. Yes. You can see like we're going to use, I mean, that's where we use it. Okay. And then, so we have proved this. Now what I want to do is, I want to compare maybe the risk of, or the variance if you want. Let's compare the variance of eta to the variance of, so this is really the risk of eta, right? Because eta is unbiased. And we know that the risk of eta is less than or equal to the risk of delta. Why is that the case? What? Rob Blackwell. How about if I do this? The variance of this is equal to the variance of eta prime. Because we showed that eta and eta prime are the same. And this is going to be r of theta and eta prime. This is going to be less than r of theta and delta prime. This one is also true. This is still Rob Blackwell for delta prime, right? This is true because eta prime is unbiased. This is true because we showed that eta and eta prime are the same, right? And this is equal to the variance of delta prime. This is because delta prime is unbiased. This is all Blackwell. This is unbiasedness. This is unbiasedness. And this is what we just showed here. So we're done. We proved that the variance of eta is less than the variance of delta prime. Because delta prime is arbitrary, we showed that this guy is related. So this holds for all theta. The fact that it holds for all theta is from the Rob Blackwell. Yes.
So we showed that it's, less, or, that it's less than like any other estimator, but or that estimator, but, how did we show that it was essentially unique?
No, not yet, but let's say that so far it's good. Right. So far it's good. So we showed that if you pick delta and you do this procedure, it is. First, this procedure produces the same thing. And let's say it's up from delta and you do this, then it's gonna be U of U. Eta is gonna be U of U. Now the question is like, okay, could there be some other U of U, not necessarily eta? So let's see if that's so this argument is exactly what I have here. Yeah, now I'm gonna notice something here. So uniqueness. So if delta prime, so that's if delta prime is where we get and it's not a function of t, this procedure that we do, this normalization is going to be straight. Because here, any delta prime conditioned on the sufficient statistic, sorry, complete sufficient statistic, I get that. And if these two are, so if eta prime is not a function of t, or in other words, if this procedure produces something different than delta prime, then it's going to be strict by the strictness of all of that. Because we're working with the quadratic loss. So then delta prime is strictly dominated by eta, so it can't be U of U. So if you have a U of U which is not a function of t, this normalization creates something new, and so you have strict domination. So that can. So the U of U has to be a function of t, and then it would be equal to this eta prime, which would be equal to any other localization. So if you kind of like think about this, uniqueness follows from the strictness of Rolle-Blackwell for the case where this procedure of conditioning produces an estimator which is not exactly the same as the origin. Sounds good. So this sort of sums up a lot of discussions that we had. And it's like the culmination of all the things that we have been doing, so completeness, risk, sufficiency, Rolle-Blackwell, domination, and visibility. And so it's all like overall a very nice result. Yes. How do we know which one?
You say variance? Yeah. How do we know it's?
How do you know eta is a bias? You guys know. So eta is created like that. Yeah, the power property. So if you take the coefficient of both sides, the coefficient eta is the same as the coefficient delta. Delta is a bias, so the expectation of eta is the same g of t. So expectation of eta is equal to the expectation of delta given t, which is expectation of delta. This is power property or smoothing property. And this is g theta. Okay. Questions? Okay, I assume it's clear, sort of. So let's see an example. So this result gives you at least two ways of construction of a UMU. One from the statement they propose an estimator that looks like this, HFT and then find edge. On find edge by setting the expectation of ht to gt. It gives you an integral equation that you try to solve. The other approach is via this proof. The proof suggests that if I start from the unbiased explanation, if I do all factorization, I get the URV. So let's try that first. So this is one approach. So let's say proof of Lehmann-Scheffé suggests the way of constructing UMVUs. So we have the Bernoulli trial example or coin tossing. And let's say we want to estimate the theta square. The square of the probability of coming of heads. For some reason, we want to do this. Okay. So maybe more complicated. So the summation of x sides is completely insufficient. This follows from a general result for exponential families, which we'll talk about later. The fact that it's sufficient is we have already seen. Minimal sufficiency you can also prove the fact that it's complete with consequence of that general result. So let's assume that. Then I need to find an unbiased estimator. And this particular one is an unbiased estimator. So x1 times x2. So why is that an unbiased estimator of theta squared? Yes. Yes, so they're independent. And each one of these expectations is theta. So it's quite easy to construct an expectation estimate of theta squared, unbiased estimate. But it's not a particularly good estimate, or all the other. So if n is equal to 2, it's good. Like if not, then no. So the plan is to condition this on the summation. So let's see if this is easy or not. What we can do is I'm gonna propose that we consider this. Let's say first just condition this u on t equal to t. So this is saying condition expectation of x1, x2 condition on the summation I from 1 to n being t. So that's what we want to calculate. And we know that if everything is true, this whole thing should not depend on theta. It shouldn't be dependent on theta because t is sufficient. So I get a proper estimator. So how do we calculate this? No, how proper is going to condition? Maybe it works, but there are easier ways.
One is two, can be 0 or 1.
Yes, they can either be 0 or 1. So they're either 0 or 1, and so this whole thing is going to be either 0 or 1.
And then you put the solution.
So first, let's figure out. Let's say I can write this as simpler. This is going to be probability of what?
Oh, they
And it's going to be the probability that they are equal to 1, because it's just a binary variable. I get 0 or 1. If it's 1, that's the probability. If it's 0, it's just 0. So that's the first step. Then you can think of this, what it means like for the Bernoulli trial. So what I'm saying is that I'm doing the Bernoulli trial, and so the n trials, and the total number of ones is t. In order, like, bunch of zeros, bunch of ones, and the total is t. When I want the first two to be 1, the first t has to be bigger than or equal to 2, otherwise this is 0. And then these two I'm gonna fix at 1. So what I'm left with are t minus 2 ones that have to distribute among, sorry, t minus 2 ones that have to distribute among n minus 2 positions. Or t minus 2 ones in there. So how many ways I can distribute t minus 2? Yes, and minus 2, choose t minus 2. There are this many ways. And they're all equally probable because of the symmetry of the problem. Right? So this probability is going to be, so there are this many, and in each one of the cases has probability, which is right. There should be no theta. This is a good event zone, right? And then let's say this intercept with that. And what is the chance that the observer
Choose T.
and choose T? So this would be, this is like the intersection even has this many things, and then the whole thing. Right, so the intersection even has this many, and this event itself is probably this thing. Well, actually, not the problem. It cannot, right? Right, so so if you convince yourself, it should be choose T, yes. So it should be n choose 2, sorry, yeah, n minus 2, choose T minus 2, and then choose T divided by that. And if you do the simplification, it turns out to be a times T minus 1 divided by that. If T is bigger than or equal to 2, and if T is less than 2, then it's going to be 0. But the nice thing is that this is automatically going to be 0 if T is 0 or 1. So I can just drop the other one. So that's the final result. So this is really the UMV. I'm just now going to, this is a function of T. If I evaluate it at the random T, so T divided by T minus 1, the T times T minus 1 divided by N minus. This is the UMV. So UMV. Sounds good. Yeah.
So I just think it's interesting that we took just 2 data points and we were able to construct this estimator. Could we have done that with any arbitrary xi, xj in this, or did it have to be x1, x2?
So what do you guys think? Did it have to be x1 and x2 or?
It should be the same. It's IID.
Right, the IID. So the different ways of arguing, the IID so the exchangeables, you can just use them, make the extra IID state the first ones. Or you can just argue by symmetry, just like conditioning that we pick this calculation that we do, you just fix position I and j to be 1, then there's no n minus 2 position, n minus 2. So everything sort of is symmetric. But yeah, by exchangeability, it doesn't matter which one you pick. Yeah, the interesting thing is whether there is any other non-trivial way of constructing a bias estimator other than this. But if you find some other way of doing it instead of just shuffling things around, then it would be nice to condition and get the same thing. But I'll leave that as a potential exercise. Yeah. Questions?
Yeah, I just had a question about that second bullet point versus T was the sum of xi is completely sufficient.
Yeah.
General result. Did we ever like formalize that?
We're going to talk about exponential families, and we're going to talk about this soon, hopefully. Yes. or maybe, okay, let's go with that. You're first.
So what you're saying is if you take some other unbiased estimator instead of U is X1, X2, right, X times J, you should arrive at the same result.
Yes, that's the idea. This is a pretty strong statement. So you try a different estimation again. Either you are wrong or the sphere is wrong. But, it would be either way, it would be interesting. Yes.
The closed form solution. Basically use. We basically use the intuition kind of like for the trials, right, to get that closed form solution, but yeah, conditioning on.
Yeah.
But it doesn't seem as trivial for any exponential family, because you know how, or at least I still was trying to write down the probability distribution with the data. It doesn't seem as obvious to me how to reduce it to a similar form for other exponentials.
Even other exponential families.
Or sorry, yeah.
Yeah, so you can talk about exponential families. So there are other ways of doing the UMV research we talked about it. But in general, yes. But if you want to, the short answer is this calculation may not be possible in closed form. So it might not be easy to calculate in closed form. But in principle, this is UMV. So even if you say can approximate it or do it by simulation or whatever you want to do. So potentially in practice you can even do it by simulation. Right, so you can generate and then condition on this. So there are a lot of approaches. So it just gives you a way of constructing the estimator, whether or not it has a closed form.
So you can have a UMV estimator, but not necessarily one that's right. Like this is pairing it's not that.
Right, this theorem is not saying, I mean, it's very hard to prove a result that something has closed form, because closed form mean different things for different people. So someone might be happy with this statement, right? This might be close enough for them. Someone might like this, and someone might stop here, right? So, yeah, you can't, like, as far as I know, say the theorem that there is a closed form solution for something, because it's not well defined. It just says that there exists one, and it's just a function of t, right? In simple cases, you can drive it up to a form which is satisfactory enough. In other cases, you might have to resort to some other method. Any other questions? Yes.
So from the theorem that we use, we're just requiring that there exists a complete sufficient statistic.
Yes, and there exists at least one unbiased system.
Right. Does it require that that there is, okay, could there be more than one complete sufficient statistic, and would you get to that same result?
Yeah, so these are again so if you complete sufficient statistic. Can there be more than one complete sufficient statistic?
They wouldn't be functions of each other then.
Yes, okay, so that modular bimation, I think that's people actually cannot hear. So yes, so there may be modular bimation. So it's like there could be some other one, but it is bimation to it. Oh, okay. And this result, the end result is going to be unique because the model for this is going to be a function of the other one, so this is going to change. So that the overall thing is the same. Right. So potentially, yeah, I can have, for example, t, if it's t complete, is 2t is also complete. So what happened is if it was ht, now it's going to be h2, sorry, 1/2 times 2t, for example, and this new h1/2 t, this is my new h, okay, but the overall thing, yeah. So it's hard to say it's unique, but marginalization. Everything is fine. Sounds good. Let's do another example. So here's the approach two. The approach two is we have this uniform zero to theta. We know that the max is completely sufficient. This one you actually proved from just first principle. And UMV is we want UMV for general to data. So that's specified data. Whatever you want to pick, you can pick. The only thing I'm going to use is that you don't use the new function and the probably sufficient, which is the maximum. Yeah. So Lehman Shafei essentially said if you can find a function of a complete sufficient statistic which is unbiased, then you're done. Okay, so what I want to do is I want to solve this. So I'm going to write down the condition for unbiasedness, which is going to be that. And we have calculated, so this is like h of t, right? So that's my t. And we have calculated the density of this. If you remember when we proved completeness in that example, we calculated the density of t. So what this is end up being is, sorry, so this is really t. So this ends up being expectation is like an integral, right? So h of t, 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 t. Actually, this depends on theta as well. Let's say ptf and theta dt. Okay. So that's the density. This part. Oh, sorry, this part basically. That's the density. And so you just get an integral equation. Okay. Now I have to solve this. I have g theta. That's my prescription, whatever I want theta squared, theta, whatever. And then this side is an integral of this. In this particular case, you know how to deal with this. So you multiply both sides by this one, so I get something like theta n over n. G theta is integral 0 to theta t n minus 1 ht dt. And then what is the idea here? Derivative, take the derivative. So d theta, theta n g theta is going to be, if I take the derivative, it's going to be theta to the n minus 1 h theta. So this has to hold for all theta bigger than 0, so I get that. And so my h theta would be 1 over theta n minus 1 d theta, theta n over n g theta, which you can just evaluate generally. And it gives you a functional form. Okay. For example, g theta is theta. And if our calculation is correct, then h theta would be 1 over theta n minus 1 d theta n plus 1, if I'm hoping that I'm not making a mistake. Yeah, what would happen if I differentiate this? I get n plus 1 over n theta n, right? And then one of, like, most of them cancel out, one remains. So I get n over n theta. That, yes, okay. So that's h of theta, but that's a functional form. So you apply this to t, that will be your UMV. Right, so what this suggests is that this estimator is UMVU for theta. And the MSE turns out to be, you can do the calculation similar to the one that we did last time. So you know the distribution like T over theta, theta, and then one. This is gonna be unbiased by construction. And you know, make a quick one, but this is like the inverse of the mean of a theta and then one. So if you have a theta distribution and then one. The mean is n over n plus one. So the mean of this is n over n plus one times theta cancels out, so this is really unbiased. It's not true because that's how it's calculated. And then we calculate the variance, in terms of the variance by that. And so this has the same flavor that we saw last time. So this is like 1 over n squared. Goes down like 1 over n squared. So this is the best estimator in the MSE sense, among all unbiased estimators. And you can construct an MSE, like an estimator that does slightly better in terms of the overall MSE by introducing some bias. So if I like look at these scaled multiple of T, similar things that you've seen in the homework, you can adjust A such that you give this better MSE. So or if you do this out yourself, you take n to be like that, then the MSE would be like this, which is slightly better than that. You can verify, but of the same order basically. And asymptotically, the difference vanishes. But this suggests that goes back to your question. It's not that this is necessarily the best among all possible estimators in terms of the risk. It's just the best among all the ones that are unbiased. Okay. You can see it's a pretty interesting result, and it's pretty, in general, it's pretty technical to be able to drive these. So in simple cases, you can do, but effectively you're like either solving an integral equation, differential equation, or doing these conditionings. So if you're expecting to get a closed form, problem should be fairly simple. But otherwise, you can do other things. So you can try to approximate this equation or do it in some other way. Sounds good. Yeah.
Practice. People choose based on the view of the requirements.
I can't give you a good answer here because I'm not sure who actually uses UMVUs today. So, so you have to ask. So these are classical things, and then for like univariate problems, if it exists, it's a very good estimator. But most often, for example, like current problems usually have a multidimensional character, and if you care about the MSE, you introduce some regularization, and regularization introduces the bias, so everything sort of goes out of the window. Yeah, I mean, I'm not a good person to answer that question because I haven't really been in practice. So, but if you care about unbiasedness, so if you want something which is unbiased, and if the problem is simple enough to be able to calculate this, then I think this is good. If you really care about the MSE, then that's a different issue. Okay, sounds good. Okay. Okay, we're done with your views. No questions. Last chance to, yes.
Wait, if we go all the way, possibly over loss, like. In the proof. Right, proving, you're gonna use and.
Yes.
So, where does this say anything from H? Because the theorem says anything from H.
Right. So this eta that we constructed, if you recall, the conditional expectation is a function of when I perform this. This is getting the function of T. The fact that theta is constructed like this has to be constructed. Right? Go back to like our interpretation of conditional expectation, it becomes clear. So this is the best approximation from delta on function of T, so particular expectation. Okay. Any other questions? Happy or not? Okay. Okay, so let's start talking about these exponential families that have been coming up. So this is a change of gear, essentially. We are basically talking about the general parametric family, which is nice, and a lot of things are known about it. And classically in statistics, they have been very important in constructing parametric families. They're so important. So it gives you a nice way to generate the parametric family of the solution in a space, whatever space you want. And the idea is like, I have a general sample space, a general parameter space. I want to build a parametric family on this space that has, like allows me to model some probability distributions with a particular parameter and take the data. So this gives you a general recipe. So the idea is that I'm going to map this general sample space to RE by some function T. And T here is going to be, this is going to be like, okay, so it takes the general X or abstract X. And I'm pretty easily very on V. Similarly, my parameter space can be abstract. I'm going to map it to RV by some other function theta. So parameterization of the model. So theta is going to be theta 1 theta theta. So there's also a result by vector. Now because I'm RV, I can take inner product of these. Okay, in the original spaces, there might be no inner product or addition, etc. But once I map them, then I can take the inner product. There's going to be also a measure on the original space. Let's say if this was RD solve or like some whether like maybe then they were counting for usually is that and a function h which translates to our plot. I'm gonna give it the way I construct this family as a dominated family with respect to nu. Or h nu if you want. If it has this parametric form for the density. Okay, so exponential of the inner product of eta theta and t of x minus something that allows me to normalize this to be a probability distribution, and then this x, h of x here. This is called an exponential family because you can see there is an exponential here. And it's a family of distributions because I have parameter theta that I can vary. And at this point, we don't know if this is really density, but this allows me to make it a density. So we'll see. And this inner product notation is just what I put it here. So it's the Euclidean inner product. So if you have two vectors A and B, the inner product is, you can think of it as if they're column vectors A transpose B, or I from 1 to D, AI, BI, if A and B are both in RD. So the key part is this, and it's like exponential. This is very normalized, and this is to allow like some part of the space to be masked, something like that. So if you look at this enough, you recognize it really constructed this. It looks like in factorization here. Right, so this is like some gt of t of x, g theta of t of x, and this that's the h of x. Is already in the factorization form or format. And so T of X is going to be sufficient by the constructed and what factorization. So it's an exponential family with sufficiency to T, parameterization eta, and the new we usually ignore, and H we also usually ignore. Sounds good. So we're gonna study this a little bit. It gets a little bit more familiar as we go. So here's like a summary again at the top. So this A theta, I haven't specified as an ingredient because it is determined by the other pieces. So it's automatically determined by the eta and the other extension and the language. So the way to see that is to try to integrate this. So we know if this is a density, if I integrate it against the new B, let's call this new. So this has to be 1. Okay, and if this has to be 1, I'm going to write it like e to the eta theta t of x, and then e to the negative a theta. This is valid, and then h of x d nu of x. This has to be 1. And then this thing comes out because it doesn't depend on x. And so I can multiply both sides by this quantity. I get integral e to the eta theta t of x, h of x d nu of x, e a theta, right? And then I take the log. So I'm going to take the log because I'm running out of space. I'm going to take the log. I get a theta here. Okay, so the log of this integral is a theta. And sometimes I write h of x d nu x as just d nu tilde. This is a new measure. With density with respect to that. So that I don't have to carry this h around. So that's the final result. So this is going to be log integral. This is like exponential against the new measure. You can just plug it in if you want. So this is called log partition function. At least the log is clear why it's called log partition function, because this is related to statistical physics. So they can think of these as Gibbs distributions, etc. But log partition function, or statistician might call cumulative generating function, because derivatives are due to cumulants. We'll talk about that later. Cumulants are similar to moments, like relatives of moments. Okay, so that's the formula. And because this is positive, this integral always makes sense, but it could be infinite. If it's infinite, it doesn't help. This means that we can normalize this. We really care about cases where the integral is finite. In other words, where a is finite. So once I specify these ingredients, there is a natural, I'm going to call it actual parameter space. This is not, I'm not going to call it natural because natural is something else. And actual is not standard parameters. The actual parameter space is all the theta space. This is finite. Okay, you started from some omega, you had some functions, etc. But these densities might not work for all omega, but like only for a subset, this might be integral. And that subset is really your parameter space. So we're going to work with this parameter space, which is where a theta is finite. So a theta first is completely determined by the other ingredients, and where it's finite, it determines the actual parameter space that we work with. And that's sort of the basic idea, okay? The parameterization or the representation is not unique, so I can change theta and t and this might get the same pattern. So the easy way to be able to scale this by a constant, scale down this by that same constant. And so t could be different, eta could be different, but I can shift eta around and so on maybe. And so it's not unique, but that's fine. There's a canonical and natural parameterization we'll talk about later. But these are the basic building blocks. Okay, so building blocks and normalization questions so far. Yes,
When you were writing out the calculation for E of theta,
yes.
could you explain how you got that E of A theta on the other side of the equation?
So this can come up in the
Oh, it's a constant. Oh,
yeah, it's constant, and then you can multiply both.
I see, okay.
E to the A theta. Good.
I apologize, I thought it was a function.
No. That's. It's a little bit small, so yeah. It's a function of the parameter, not the function of. Okay. So you're integrating this with x. A theta is constant. Okay. What else? Okay, so let's see an example. Like, let's say this the Bernoulli is one Bernoulli variable. So here the underlying measure is the counting measure, so the density of or the mass functions and find the 0, 1. So that x you can take as just 0, 1. And you call that this is a nice way of writing down here the Bernoulli variable. And so if you do some algebra, it can be written in this form. Exponential x, you recognize it as t of x. Inner product, in this case, is just the usual product with eta of theta. And then this, you can recognize it minus a theta. There's not much integration here, but just summation to 1. You want to sum to 1. And so that's one way of stating this as a representing as an exponential family. So eta theta, theta, and then this actual parameter space the way I define it has to be strictly 0 to 1. It can be 0 and 1 because the exponential would you get into trouble. So these PMS have to be positive, strictly positive, because it's exponential can be 0. And you can see here, I can't take theta to be 0 or 1. So the family will be defined, well defined as an exponential family over the open interval 0 to 1. Okay. It's also an easy result once you have something as an exponential family. If you take IID samples, the joint distribution would be another exponential family. And that's sort of easy to see from the definition. So here's another example. So this is, okay, so I probably forgot to mention, there is a dimension or rank. So did I mention it here? So the dimension of the family or rank maybe, dimension would be D, okay, D-dimensional. So in this case, this is one-dimensional. Here's another example, which is two-dimensional. The usual normal distribution with mean, mu, and variance sigma squared. Let's take it into theta. And so you know the density, that's the density. And you do some algebra, just expand, collect all the pairs that are functions of x, and the rest is here. So if you look at this, you recognize that this can be written as the inner product, right? So different ways, but let's say I consider mu sigma divided by sigma squared, and then minus 1 over 2 sigma squared. And this inner product with x and x squared. Okay, so if I write it like that, then t of x is, this is t of x, and this is eta of x, eta of theta. So t of x is really, it's just t is a map from R, in this case, to R2. So that X here is just R, okay? So mapping from reals to R2. So it takes basically infinite square, basically the first, the second order polynomials, like moments if you want. And then you have theta, take the inner product, and then you recognize that this is perhaps an A theta. And you can see that this has to be there for this to normalize to 1. That's where this comes from. Really, the like Gaussian is an exponential family in the real line. We give insufficient to this. And it has to have 2 parameters. You can see I can become really defined parameters, both things. These are not the natural parameters, but the parameters that you know about, like you see the square. They have situations so they can map. You're basically mapping theta, which is mu sigma squared, to this thing, which is eta of theta, like mu over sigma squared. So this mapping is the parameterization eta. So this is A theta, and you can see that this is, so you know implicitly that the sigma squared has to be positive, mu can be anything. So, so this is where this integrates. So we can actually see also from here, the sigma squared has to be positive, otherwise it doesn't make sense. And you can limit. So that's the actual parameter 6. The sort of all mu and sigma squared such that sigma squared is bigger than 0. So the uniqueness sort of you can also see here. I can, for example, non-uniqueness. Pick this part and call it h of x. Then A theta would be a little bit different, but so we have an exponential family. So that there is some sort of freedom in choosing how to represent this as a. Sounds good? Okay, so we have a little bit more time. Here's a non-example. So uniform 0 to theta, that's one of our classical examples. This is not an exponential family because the support depends on the parameter. And a feature of this exponential family idea is that the support the exponential cannot be 0. So this is then all positive. So the 0 of this doesn't come from theta. This would force things to be 0, but this is not dependent on theta. So a family whose support is variable cannot be an exponential family. So this is out. Okay, in the remaining 2 minutes, maybe I just want to mention this and next time discuss this. So we are going to put some regularity assumptions on these families. The first one is that, again, this omega naught is all the thetas for which A theta is finite, what I'm calling actual parameter space. The eta maps this to RD. Under eta, this gets mapped to some set. You want this to have non-empty interior. So if you have seen analysis of what the interior of a set is, not just review this, but just Google interior of a set. And hopefully get familiar with this. So we want non-empty interior. So sets that have empty interior would be problematic. And we also want statistics. So remember, these are essentially functions of x. So I want these as statistics and also 1. So these are the coordinates of this M1 to be linearly independent. New almost everywhere, or new tilde. This is including h as well. So if you ignore it, you're good. Okay. So what I don't want to happen is there shouldn't exist in A and C such that some of them are non-zero for which this identity holds. So I don't want to be able to write an affine equation among these, okay? In other words, I shouldn't be able to write one of these as a linear combination with the other ones, almost surely. Almost surely means stochastically everywhere is true. So these two conditions would be very helpful. There's another condition which is slightly milder, sorry. Eta of omega naught is open, then it can find some more. So that sometimes is enough. So a family that satisfies E1 and E2, you'll call full rank. Full rank exponential family, and we're gonna work with these families. These have the nice properties. There are some other terminologies that we have to find. Some people call it regular. We have this between people call it minimal. These terminologies are not consistent. Some people sometimes call it differently. So E2 is very interesting because it prevents identifiability. So if E2 fails, the model could be non-identifiable. You know this something like the overflow. And E1 prevents AI from satisfying a constraint. So next time, what I want to talk about is this result. In a full rank exponential family, that sufficient statistic is complete. This is the result that we have been using. And we're going to prove a partial proof. We're going to actually prove that P is minimal. Proving this complete is a little bit harder. But we'll talk about that. Okay, so this is the result that I'm going to talk about it next time. So these conditions are to have that result. Questions, comments? Okay, thank you guys. See you next time.